we are continuing with bending stress. Very important, beams are the primary, well, the main structural form we use today. How do we design our beams? Well, it's all based on stress, and once we calculate our stress, we know it has to be less than the yield stress. And you know all about yield stress because you've come across it in Project 1. So in order to calculate our maximum stress, just going over this again, these two terms here, M would be to get maximum stress you would need maximum moment, and this is moment of inertia, which we'll discuss shortly. But these two values at a point are effectively constant. So just once again repeating, therefore our variable is y. So what is y? If we have a beam with some load on it, when it actually deflects down, we get a triangular stress distribution. We get tensile stresses at the bottom because it's stretching at the bottom. We get compressive stresses at the top because it's squashing. And what y is? It's the distance measured up and down from the neutral axis. Because our neutral axis is where we have zero strain and zero stress. That's what the neutral axis is, the centroid of the section where you have no strains or stresses when you're bending. So thus, where is stress maximum? When is stress maximum? When both your moment and your y value are maximum. So these need to be maximised together. So where are they maximum? At the top and or the bottom of the section. So just be clear. As I said, 1 year in an exam, I drew a section and I didn't ask for the maximum stress. So this is my cross section here. It was just a rectangular section. But I said, tell me what the stress here at point B is, where that's a distance 50 mil up. And then it became apparent that people didn't really understand the form of this equation. How that is the equation for this line in here. It's linear, ky, maximum stress at the extreme fibres. Okay, so we did go on using that formula and we worked through the procedure that you would work through when you come to do Project 3, which I'll brief you about after the mid-semester break. The process being you draw your, in order to draw your bending moment, you draw your shear force diagram. Oops. You calculate your maximum bending moment. Then based on our section, we work out our moment of inertia here. And then plug it into our formula. Stress is my on I here. We calculate a stress. If it's less than our yield stress, our beam is considered safe. So quite a simple process to run through. That was for a solid rectangular section, so I've now got an example on here, and I believe that's where I was rushing through. Shh, guys, you've come to listen. Please listen. Well, maybe you haven't come to listen, but please be silent. Okay, this time our section is a rectangular hollow section. And the formula we used previously for I, for a solid section, was BD cubed on 12. And again, we will talk about this shortly, where B is always parallel to your axis of bending. And the axis of bending, when you're looking at the cross-sectional area, is the axis that divides the region in compression from the region in tension. So people say to me, why is the axis of bending? Is it horizontal? Is it vertical? I say, imagine how something bends, and it's the axis that divides what's stretching from what's squashing. So in this case here, that axis would be running through the entire midsection of this beam, and related to the cross-sectional area here, it would sit horizontally. So when you have a solid section, it's BD cubed on 12. When you have a hollow, it's BD cubed on 12 of the outer minus BD cubed on 12 of the inner. And you came across this when you did buckling. Remember when we did buckling, our formula was EI pi squared on L squared. And for I, you were given various values, so you were told about the BD cube. So for this particular section, we work out our I value. We know our stress will be maximum at the top and the bottom of the section. We now need to find where our moment is maximum. So from our loading, you would of course first work out your reactions. Based on those reactions, you would draw your shear force diagram. And from that shear force diagram, you would draw your bending moment diagram. So before I stick up there, before I put the bending moment diagram on there, let's just work through. What's it look like? Shear is equal to dm dx. So when we have a positive shear, that equates to a downward slope in our bending moment diagram. Downwards because bending moment is positive down. So normally you think positive is an upward slope. Now positive is a downward slope because we draw bending moment down positive. So by having a positive shear force diagram here, I know it is a downward slope, then my shear force is negative, so my bending moment will be sloping up, and now my shear force is positive, so my bending moment is sloping down. And that's the procedure I go through when I draw my bending moment diagram. I go positive up, negative down, positive up, negative down. Then I say to myself, where is my bending moment 0? Well, it's 0 at a pin end support, so the moment is 0 at a pin end support. It's 0 here at the cantilever end. Yes, I have a roller in here at B. However, my beam runs continuous over the roller. So the reaction is only vertical, but there's a moment in the beam there. So knowing where it's 0 now and knowing how to join the dots, well, I join them up. It's 0 here, I have to slope down linearly. Now, why am I sloping? How do I know my bending moment is linear? Well, if V is equal to dm dx, m is equal to the integral of our shear force. If our shear force in this case is constant, when we integrate a constant, we get a linear expression. Or you can simply say, if I consider a free body diagram cutting through here, my force is 10, my distance, say, is 4 metres. I draw my unknown shear, moment, axial force. What is my moment equal to? Very easily you can see it's force times distance. It's linear. So we get our value here, 40. How do I know it's 40? Well, I can calculate that 40, as I said, based on my free body diagram here, because that moment here would be 10 times 4. Or I can base it on the area under the shear force diagram graph, and that area there is 40 also. So I would go from this 40. I wouldn't draw the middle bit next. I would start from the right-hand end, point D. My moment is 0 at D, and according to which direction it slopes in, I know it has to slope up. And then I would join the dots in the middle and say I know it's straight in between. So how did I get this value of 80 here? Well, I could simply cut through the beam 4 metres in. Here's my free body diagram. I've got a point load of 20 kilonewtons, and I'm cutting it at 4 metres. So very easily, looking at that free body diagram, you can see the moment there is 80. Or if you wish, you can work on the area method. However, when you work on the area method, that area is a positive 80. So what you have to realise, if you come from the right, the bending moment is equal to the negative of the area. Okay? So if I call that area 1, that area 2, that area 3, this moment down here is equal to area 1. This moment up here is equal to minus area 3. Or if you come from the other direction, it's equal to area 1 minus area 2. Okay? Okay, we have a bending moment diagram. We just plug in, our maximum moment is 80, my maximum Y value here is 175, and we end up with our stress, maximum stress, which is the same at the top as it is at the bottom. So that's cool. However, if you have a section that is not symmetrical, as shown here, a T section, where is my neutral axis? Is it closer to the top or the bottom? Top. So you all know instinctively it's closer to the top. I will show you exactly how to calculate where it occurs in the next hour, but it is closer to the top. So thus now, when I look at my stress formula, My on I, what do I put in for Y? Well, if I want the stress at the top of the beam, I would put Y topping. So for metrical sections, the neutral axis lies at the section centre. So your Y top is the same as your Y bottom, and thus the stress at the top is equal to the stress at the bottom. However, for non-symmetrical sections, as the T section shown, we need to find the neutral axis before we can proceed. So if I was to draw that triangular stress distribution for this section here, for now, I'll give you the y value. The y from the bottom, so this distance in here is 365.5 millimetres. And because we know our section is 520 deep, our top value, y value here, is 154.5. So we have different y values. So tell me, where will our stress be greater now? At the bottom, always at the bottom. So in this case here, the stress value here at the bottom, the maximum stress value here at the bottom, is simply equal to our moment from before. Let's take the same moment times our length of 365 divided by the I value given to us over here, and we get a stress value of 114. When we work out the maximum stress at the top, well, of course, we use the distance to the top, 154, and we get a stress value equal to 114. So, just mentioning, which I haven't mentioned again today, your units, that's meant to be an I. I like working in megapascals, and to be working in megapascals, I will have units of millimetres to the fourth. My moment, I will convert from kilonewton metres to newton millimetres, and my y value is in millimetres. So, in this question, if you were asked, yep?
Why is the yield max at the same value?
Oh, have I written the same value? Because I read it off the page wrongly. Thank you. No, I wanted to check whether you're awake. Yes, I read it off the page. It was lovely in my second YouTube that I've just come from. Someone was saying, oh, I make lots of mistakes. Lizzie, can you give me some tips how not to make mistakes? And I say, I make mistakes all the time. And he quite lovely said, oh, no, you must be so smart. You'll never make any mistakes. And I'm like, I make them all the time. Anyway, so in a question like this, you didn't need to know that, but hey, bit of light relief. No, that wasn't a mistake. That was, of course, done on purpose to check you were still awake, because I never make mistakes. In a question like this, you may be asked, what is the maximum positive bending stress? So what is the maximum tensile bending stress? So that would be the bottom stress in this case. What is the maximum compressive bending stress? You may have a material that's not steel. It may be cast iron or something that has different yield stresses in tension or compression. So it's important to recognise that they have where the tensile stress is and where the compressive stress is. And before you come and ask me where they are, of course where they are is simply gained by looking at the deflected shape. Remember what I said about the deflected shape? We always draw our bending moment on the side of the beam that's in tension. So if I draw my deflected shape there, I know I have stretching in the bottom of the beam. When I bend this ruler, the bottom is stretching. So where my moment passes through zero, what does that correspond to again? A point of inflection. And thus I know I have tension on the top here. So actually I was wrong there, wasn't I? Did I write tension in the bottom? In this particular question, tension is at the top of the beam. So before, again I was checking you that. Top, so this is a tension stress and this is a compression stress. Can you see that? Because at that location where my moment was 80, I actually had tension in the top of the beam. So I think I was telling you before that our tensile stress is in the bottom. It's actually in the top. So far, so good? Good. Okay. Oh, there you go. Stress at bottom will reach yield first. Okay, it will reach the yield first. Cool. Oh, there you go. I've done it. Okay, we're going to move on. So you need to know all about I now. Moment of inertia, more correct second moment of area. So please don't get the moment of inertia muddled up with inertia that you use in mech-eng. They're two completely different things. So the more correct term is to call it the second moment of area, and that is because if you look at what it's actually equal to, it's equal to the integral of y squared dA. You know y is the distance from the neutral axis, and dA would be that component of the cross-sectional area at that point. Our first moment of area, so the first moment of area would equal y dA. Area times distance. Second moment of area, y squared dA. So I derived this expression for you last week when I derived the formula that stress is equal to my on I, and I derived that expression for you by considering what our resultant compression and tension forces were when we considered the bending stress distribution. So this is the bending stress distribution acting down the cross-section, and we have a triangular stress distribution, in this case compression at the top, and thus that means we have a compression force pointing to the right and a tensile force pointing to the left, and of course because all the forces in the x direction equal 0, the two forces combined will equal 0. However, we can calculate moment using these expressions for C and T, and we arrive at the formula that I is equal to the integral of y squared dA. Boring. Let's get on with it. Okay. That's what it looks like. And all the values for I in the tables, the section tables you've used for Project 1, have been derived using that formula. Now I say that because when we do it in class here, we assume all our corners are not radiused, that they're straight. So it is correct that I is equal to BD cubed on 12 for a rectangle. However, if you have a very odd shape that looks like so, you would actually have to work through the integral sign and actually calculate what the I value is. So what I will do is I will actually derive the value BD cubed on 12 for you to show you how it is derived. So before we do that, as I said, you have met this I value before when you did buckling. So what is I? You should actually have a feel for what I is. You should be able to feel I in the air. It's a geometric property. So my bit of moulding here, it has a length of, I've written on it, 950 millimetres long, and we know it has a certain thickness and it has a certain width, and if I say where's the cross-sectional area, you know where to point out the cross-sectional area. Well, it also has a stiffness, depending on which way I try and bend it. So I want you to think of I as, what it does is it describes the bending stiffness. So if I have my ruler this way round, we know it's not very flexible. It is very flexible, so it's not very stiff. However, if I turn it round, as shown, and I try and bend it, it's a lot stiffer. So I want you to think of it as measuring how far the section is spread from its neutral axis. So when I position it horizontally as shown, my neutral axis is horizontal. Can you see the area sits very close to its neutral axis? However, when I rotate it now 90 degrees and I imagine my horizontal neutral axis, can you see it's spread far away? So that's effectively what stiffness is. It's the spread of the area from the neutral axis. So here we have two sections. One is a solid rod, one is a circular hollow section. They both have the same area, so they both weigh the same. However, of course, my circular hollow section is spread further away from the neutral axis. So if we do plug in the formulas, you can see it's actually 8 times stiffer. So when you get to the problem set questions, it's going to give you about 10 sections, and you should be able to look at them and imagine which one is really stiff. So if I do now draw my I-beam here, and I put my neutral axis in, can you see how that I-beam is comprised of a lot of material far away in the top flange and a lot in the bottom flange? So an I-section is a relatively very stiff section. So why is it the shape it is? Because we're trying to move the area far away to make our beam stiffer. So when we tackle this now, we're going to look at symmetrical sections first, and then we're going to look at unsymmetrical sections. And the reason we divide them up like that is because for symmetrical sections we know straight away where the neutral axis is. It's in the middle of the beam. So symmetrical sections are dirt easy. So looking at our symmetrical section, we know because it's symmetrical, the maximum y would be equal to half the section depth here. So let's prove how we get BD cubed for a rectangular section. So I is equal to the integral of y squared dA. Now, this area here that we're talking about, well, instead of writing dA, I'm going to write b, which is the width, times dy, because b is constant. So now when I look at my integral sign, it's all in terms of y now. So if I now do integrate my y squared term, of course I get a y cubed on 3 term. And when I integrate, I'm integrating between d on 2 and minus d on 2, and plugging in the values gives me bd cubed on 12. So you just need to memorise I is equal to bd cubed on 12 for a rectangle. So when we have sections that are made up of rectangles, okay, you can very easily derive the I value, not doing the integrals again, for any symmetrical section, assuming it's made up of rectangles. So the I value for different shapes would be bd cubed, the sum of all the individual bd cubes on 12. But very, very importantly, when you do this, when you consider it made up of a number of different rectangles, the centroids of all those rectangles have to lie on the same neutral axis line. So for this rectangular hollow section here, you can say it's the big rectangle, take away the little rectangle. If you actually broke it up into 4 rectangles like so, if you added all those bd cubed on 12s up, you would not get the right answer. You have to include another term that's necessary for unsymmetrical, asymmetrical sections. So there's always a way of looking at symmetrical sections and just saying, oh, it's a sum of all the areas. Okay, so let me quickly, even though you've done it already, look at a section that's 120 wide, even though it doesn't look like it, because my 100 is actually longer than my width, but that's due to my poor pictures. The thickness everywhere here is equal to, what have I made the thickness equal to? 10 mil? No, 15. Sorry, I haven't written it down. So thus, that within there would be 90. Oh no, hang on, let me go back. I need to go back. Disorganised. In our section here, it has different thicknesses. So the thickness down here is 15 mil. And the web thickness in here is, oh, that's 15 mil, sorry everyone. And that's 10 mil. So when I look at my vertical in a rectangle here, it would be equal to 80. So I'm going to redraw that anyway. So I'm going to say that's equal to my big rectangle, 120 times 100, take away my little rectangle, which is 90 times 80 deep. Now I'm looking at bending about the horizontal axis. So when I do look at the centroid of all my rectangles and my initial shape, they all lie on the same line. So as a result, I is just equal to BD cubed on 12 of the outer minus BD cubed on 12 of the inner rectangle, which gives me a very big value. So that one is easy enough to do, I think. My second shape here is a universal beam, a UB or an I section, we often refer to it as. So think about how I'm going to break this one up into rectangles. So that's 80. 5, and overall it's 100 deep. So, some of you may be thinking, oh, let's do that one, plus that one, plus that one. To which, of course, because once again we are bending about the horizontal axis, I would say is wrong, because the centroid of this rectangle is up there, the centroid of the centre rectangle is on the same line, and the centroid of the bottom rectangle is down there. So you wouldn't set it up like that. So for this one, and I have to try and be neat, you would say it's the big rectangle, take away. These are meant to be rectangles, by the way. These two little ones, and what I'll do is I'll dash in the flange so you can see what I'm taking away. And when we do it that way, as you can see, if I've drawn it well enough, the centroid of all these areas lie on the same line. So in this case here, I will be equal to 80 times 100 cubed minus 2 times. So this space in here, it's 80, take away 5. So each side here is 37.5. So you can either join them together and just call that 75, or you can just say 2 times 37.5 times 90 cubed on 12. And that would give you that value. Now, if that was my I-beam, sitting that way around, imagine my flange on the top and the bottom, that would be able, and the loading is down, it would be bending the horizontal neutral axis would be what we're looking at. Yep. Yeah, I'm about to just say now. So imagine this time round my beam is sitting this way around but the wind's blowing, so it's a horizontal wind load. So this time round my neutral axis, the bending axis that I'm dealing with, is that what you were about to ask me? Is that way round. So I'll call that one XX and this one YY. So if I was working out, I'll call that one XX and this one YY. So if I was working out IYY, then I would divide it up that way. Because you can see all these rectangles now have their centroids lie on the axis of bending. So for IYY, it would be 5 times 80 cubed on 12. And there are 2 of them. And then it would be plus 90 by 5 cubed on 12. Is that what you were asking me? Yeah? And if you do actually, and I don't have, oh no I do, no I don't have a value here. But if you had a value here, the element is a lot stiffer about that axis. And if you look at what you're cubing, that becomes apparent. See, I'm cubing 100 here, and I'm cubing 90. Whereas when you look at it in terms of IYY, we're cubing 80, but here we're cubing 5. Okay? So in this case here, you could say straight away that IXX would be greater than IYY. And that's why when we have these I-beams, we sit them up the way it's drawn here. Now, the only time you would see an I-beam, and you do, sitting that way round, is if your loading is horizontal. And that would happen when in a wall, in the wall of a portal frame or something, where your main load is your wind load. So, there's nothing difficult about calculating I for symmetrical sections. I'll just show you quickly how you would do it for a circle. So for a circle, you can't use your BD cubed on 12s because there's no B's and there's no D's. So you would have to use your integration. Now, if you have a look at this, if you try doing this in Cartesian coordinates, dA is that area in there. So instead of dA, we could write 2x, because that's the width here, times dy. So if I stick that into my equation, I'd say y squared, instead of dA, I'd write 2x dy. Now I still have two variables in there, x and y. But we know what the equation of a circle is. So instead of our equation of our circle, as you all know, x squared plus y squared is equal to a squared. So we could then find our variable x in terms of y. So then in here you would say y squared, and you would put that term in for instead of dx, instead of x. Now, I'm going to leave that for you to do at home. And I did myself do it because I teach it, so I have to do it. And I tell you what, it was a pain in the butt finding all the right identities and actually doing that, and it required to do it by parts, and it was a real pain in the ass. But when you do it, you get pi a squared on 4, which is the formula we gave you for buckling. Now, some of you out there who are really good at maths are thinking, oh, you wouldn't do it in Cartesian, you would do it in polar coordinates. Yeah, you would. So I can do the quick polar coordinate integration for you, because I looked that one up as well. So if we were doing this using polar coordinates, because as I said, to do that integration, it took me a whole page of working. And then I knew what the final answer was, and I didn't get there straight away, so I had to work backwards and go, I forgot how to do all this integration, and I worked through it all. So doing it using polar coordinates, okay, in this case here, instead of dA now, oops, let me find it. Instead of dA now, we could write r d theta dr, if you know your maths. And in this case here, what is y? Y is this distance here where that angle is theta. So y is equal to r sine theta. So when I write I out now, instead of y squared, I'll write that. And instead of dA, I'll write that. And this is a double integral, sorry now. So I know we can very easily integrate that because you integrate the two terms separately. So in this case here, the range on your limits here, one would be your radius, one would be 0. And for theta, one would be 2 pi and one would be 0. And anyway, Either way, you get pi r to the 4th on 4. So remember that. Okay, so that's symmetrical sections. Easy peasy. Now we move into non-symmetrical sections. We don't need a break yet, do we? Okay, I'll give you a project asking, come down and ask me any questions you want. Short break. You've got a short concentration span, some of you.
Quickly go back. You said that derivative deriving using polar coordinates in the equation, it goes down to what?
Oh no, that should be a square there. So you move that r here, it becomes a cubed. So when you integrate this now, you effectively are going to integrate sine squared theta d theta, and then you're going to integrate r cubed dr. So you can do those two integrals separately.
Is that plus or times, sorry? They multiply by each other.
Yeah. So you can see straight away here when you integrate r to the power of 3, that gives you your r4 on 4. Yeah. Which is your r4 on 4. And when you integrate sine squared over that range, you end up getting pi. Yeah?
Another quick question I had was, how are you determining what terminals to use for your integrals?
In this case here, so it's always, well, if we were doing this by Cartesian coordinates, over the area here, you would integrate from r plus r to minus r. So here it would be from plus r to minus r, because we're going, that's Cartesian.
So wait, A is pretty much radius in this.
Yes, sorry. So A is the radius here, yeah. So when we do it in polar coordinates, we're going to integrate, because when you do your polar coordinate, you're talking about that block there. So you have to integrate 2 theta, from 0 to 2 theta, and from r is 0 up to r is a maximum of r.
We don't have to prove this in an exam. Oh, thank you. That's what I was going to ask.
You don't have to prove this in an exam. If it was a maths exam, maybe you would.
Yeah, right. So I got your question for the IB.
Yeah.
I don't think I got the description what happens when the bending moment happens at not in the center, but
I'm doing asymmetric sections now. The bending moment of a symmetrical section, the neutral axis is always at the center of it. It's symmetrical.
okay.
Yeah.
I have 2 quick questions. One is with the project. Do we have to put the meeting thing on the report or separately?
No, put it into the
Put it in, okay. And because we're missing a week of tutorial questions for like bending moments.
Yeah, so that's why I said in week 8.
Yeah.
So I've
Hey,
emailed you.
I was wondering if we could like post the answers up.
The answers.
I'm not sure if I'm doing it right.
Yeah, so basically there's a file running on Moodle with all the answers in it to every piece of question, except for this problem set. Because you see an answer to this problem set is drawing the bending moment diagram. And if you provided a picture of the bending moment diagrams, we're getting everything. So I really want you to do it right.
Oh yeah, because I've done like half of it, so I'm not sure if I'm doing it.
Yeah, but you're not doing it any later than everyone else. See, next week, you're going to go to one of the other classes. Oh, in week 8.
No, I have it tomorrow. So I'm not missing it.
Oh, okay. Oh, I see. So
I just want to do it over the holidays.
Oh, yeah, actually the solutions are coming online.
Yeah, this week.
No. It's actually not until after Yeah. Sorry, no. Because if I put them online, the solutions, no one's going to come back. Yeah. If you want, you can. If you want to scan a couple in and say these are the words look right, I can say they look right in the form, but I want to check them in. Might check them in Deb. Okay. Moving on. So no, I will not ask you in an exam to prove that one, though. The BD cubed on 12 one may happen. That one's easy enough to do, but not the polar one, because then I would just be testing you on your maths. And I know you're all good at maths. It's your engineering I want. Okay, someone said to me, came up and asked me, for this section, what happens if the moment isn't in the middle? What happens to the neutral axis? If your section is symmetrical, your neutral axis is in the middle. So symmetrical sections, neutral axis always in the middle. Okay, so now we have non-symmetrical sections, and we all know from looking at it, hopefully, intuitively, that our neutral axis is higher up. So before we can proceed, we need to find where the neutral axis is. So to locate the neutral axis, again, when I did the proof of all the formulas, I actually, when I worked out that my compression and my tension force equals 0, the two integrals I had for the value of the tension and compression was EK, integral of y dA. So thus, from that, we have the fact that our first moment of area equals 0. And what that basically means is knowing where the neutral axis is. If I say area times distance, because it's rectangular, I don't have to worry about the integrals. And area times distance, one gives me a positive, one gives me a negative. That value equals 0. So we utilise that relationship, but we put it in a slightly different form here. And we do that by using a reference point. So instead of now referring, when we have our two expressions, the integral of y dA equals 0, we now express it relative to a reference point. And that reference point is usually the bottom of the section or the top of the section. So here now, instead of y, I've written yi minus yc. And you can see here that yi minus yc is equal to y. So now, with this second term in here, I can just say the integral of yc dA is equal to the integral of yi dA. Y seen being the distance to the neutral axis. And that formula can simply be written as AYC is equal to the integral of AI YI, which means absolutely nothing to you. So, this is what the formula looks like, and you have to know how to use it. To find where the neutral axis is, okay, you define a datum point. And in terms of these areas, you break up your rectangle into lots of areas. So here, area 1, area 2, area 3. And these yi values are the distances from your datum point to the middle of area 1, to the middle of area 2, and to the middle of area 3. And you divide by your total area, and that will give you a value of yc, which actually is the location of your neutral axis from the bottom of the beam. I'm going to write that up. Here it is neater, here. Okay? Sorry. No, I'll leave that scribble up there. Okay? So it's a very easy formula to use that looks complicated, but once you know how to use it, you don't even have to think about it. So this formula is, not that you care, blowing you all away, you're going, I don't really get it, but Lizzie just said I need to know how to use it. What I want you to do is I want you to realise this formula is very similar to the one you use to find resultant forces and their location. So think back to week 2. I said when we have a beam here and we have a mass here, mass 1 or W1, and we had a weight here W2 and we had a weight here W3, and I said what's our resultant weight here? Well, you all know it's equal to all the weights added up. So it's equal to a sum of all the weights, or our resultant weight, yeah? Now, in order to find that position, where that resultant was, what did you do? You said force times distance plus force times distance plus force times distance is equal to the resultant times its distant h, didn't you? Can you think back that far? Now, that is the same formula we're using to find the centre of area. So to find the centre of a group of forces is the same as finding the centre of a group of areas. So this formula would be the formula you use to find where the resultant force is acting, and that's this identical formula we use to find where the centre of the mass is acting. So the neutral axis is the centre of mass based on the first moment of area. And again, it doesn't mean much to you. Let's run it through it again. What you have to do, you choose a baseline or a datum line. It can either be from the bottom or from the top. You'll end up at the same neutral axis line. So if you worked out, if this section here is 50 deep, and you worked out that YC is equal to 30, if you were working from the top, you would have got a value of 20. So it doesn't matter where you work from. Your datum can be on the moon. Would be a pain in the butt, but it can. It doesn't matter. Just like equilibrium. You can take moments about any point because that's what we're doing. Area times distance, area times distance. So we divide our shape into rectangles and we apply our formula. Area 1 times y1, so y1 as I said here, would run to the centre of that area. Area 2 times y2, area 3 times y3. Again, doesn't mean much. Let's stick some numbers in it. Here's our formula. We're going to have our datum at the bottom. We've divided up our T section into two areas, area 1 and area 2. So area 1 here is 200 by 20 mil. 200 by 20 mil shown here. And the distance from our datum, which is the bottom of our section, our whole section is 320 deep. So we come down 10 mil to get to the centre of that rectangle, and that's where that 510 comes from. Then we look at our second area, area 2 in green there. That area is equal to 500 by 10, so that's the area. And the distance to the centre of that area is simply half of 500, which is 250. And then we divide this by the total area. And that will give you where your neutral axis is. So it doesn't matter if your shape looks like that. Okay? You would just go, I'm not going to panic. This is giving us a really stupid question on the exam. You would divide that, go, okay, I'm going to say I have one area. You can divide it up into whatever rectangles you want. 2 maybe, 3, 4, 5, 6. Or you could take it as the whole thing, take away that area and that area and that area. Oh no, that would probably be a bit more difficult. It doesn't matter how you divide it up into rectangles, okay? So, easy enough. We now know where our centroid is. So be aware, now my section is no longer symmetrical. In red here I've shown where the section neutral axis might be. If I divide that up into two rectangles, the flange and the web, can you see their centroids don't line up with the centroid of the section? If I choose to say, okay, that T section is a big rectangle, take away a little rectangle, can you see none of those centroids line up? So we no longer can just say I is equal to a sum of all the BD cubes on 12s. So because when your section is asymmetrical, you can't get all the centroids lining up. So we therefore have to use the full-blown parallel axis theorem problem. Is this something you need to know for the exam? Yes. Is this something you need to know next year? Yes. Is this something you need to know in third and fourth year? Yes. Is this something you need to know as a practicing engineer? Yes. Okay? So, okay, you don't need to know how to integrate a circle, the area of a circle, to find the moment of inertia. You need to know this, okay? So I will prove the equation. You don't need to know that bit. So just try and follow what I'm saying here. What we do now, as the centroid of all the areas no longer lie on the same axis for a non-symmetrical section, we need to determine the inertia, or the second moment of area, about a parallel axis. And that is typically the neutral axis. So here is the neutral axis of my section. So just imagine my section might be this shape. So what we do is, again, we define y. When we originally looked at our formula, this y value was the distance from the neutral axis of the rectangle. But the neutral axis of our rectangle is up here. So instead of working from there, we're now working from the neutral axis of the overall section. Thus, instead of y now, we're going to write, we're working with that length there. So we write y minus the shift value. We square that, and when we expand that term out, we get a y squared term, we get a 2 times y shift term, because you know how to expand out your brackets, and you get a shift squared term. Now this first term is equal to the integral of y squared dA. Well, that's just equal to BD cubed on 12 of each of our rectangles. This second term in here, well, this has an integral y dA, and we said earlier that our first moment of area is 0 when you're dealing about the neutral axis. So that second term disappears, and then we have our third term, shift squared dA. Now, it's all written there in integral sign. When we do this, we deal with sections made up of rectangles. So we don't do the integration. So our formula here simplifies down to the moment of inertia, or the second moment of area, about the section neutral axis is equal to, there you go, is equal to a sum of all the I values of the rectangles, and they're all about their own neutral axis. And then we have this shift term, and I'll explain what that is in a minute. Once you get your head around shift, this is not hard. This to me is the easiest question on the exam, because all you have to do is plug into the formula. All I expect you to do is know how to use the formula. Okay? So we have two terms now. The first term is easy enough. It's the sum of all the BD cubed on 12s. And we have this shift term. So here is our full-blown formula here. Now, when our sections are symmetrical, shift equals 0. Which is why, when our sections were symmetrical, we said it's just the sum of all the BD cubes on 12s. So what is shift? It's a mouthful, so I'll draw it for you to see it. But shift is the distance between each rectangular area centroid and the centroid of the section. It's not hard. So as I said, when your section is symmetrical, shift equals 0, and the formula simplifies down. And where I've got here the sum of BD cubed on 12, if any of the shapes are circles, you would substitute pi out of the fourth for BD cubed on 12 in the form it's written there up now. So again, let's do a problem. Okay, so what do you do for a non-symmetrical section? You divide your section up into rectangles, area 1, area 2. So here I've shown what shift is. Shift is the distance between the section neutral axis, the green dashed line, and the neutral axis of the particular area. So therefore I have a shift 1 value and a shift 2 value. So when you use your equation, you would say for area 1, b d cubed on 12, for area 2, b d cubed on 12, and then you would get your shift term here, square it, multiply it by area 1, your shift 2 term, square it, multiply it by area 2. And people say to me, oh, is shift positive or negative? You square it, so we don't worry about positives and negatives. Again, mouthful, let's do an example. It's the same shape we had previously, where we found the neutral axis here was 365.5 mil. Now, the easiest way to do these problems when you first start is to draw something that is in proportion. So you can then draw on your diagram what you expect shift to be. So when it comes out to be 349, you can look at your diagram and go, no, I've done something wrong there. Okay, so shift 1 here. The distance from the bottom is 3 165.5. The distance to the centroid of that area is 510. So shift 1 is simply 510 minus 365. Can you see that? So shift 2, the distance to the neutral axis once again from the bottom is 365.5. How far up is the centroid of that area? 250. So therefore you have a value for shift 2. So now for I, all you do is you add all the BD cubed on 12s up. So that first and that second term, that first term and that third term in there. We're talking about the horizontal axis. So area 1, this relates to area 1. B is 200, D is 20. And in here, this relates to area 1, where B, being the dimension parallel to the neutral axis, is 10, and your depth is 500. Then these second and fourth term are your A times shift squared. So we just get our shift term, we square it, we multiply by the respective area. Bob's your uncle, it's done. It's not hard. You just have to do it a couple of times to get familiar with using the formula. So where people have issues, they go, oh, I just don't understand what shift is. Oh, my God, it's so hard. No, it's not. Draw your damn picture. Find the centroid of your area, the centroid of the circle, draw an arrow line between it and measure it and calculate it. It's not hard. So don't imagine things are hard when they're not. Okay. That example's on there. Let's get you happening on this one. I will give you the final answer. Just find the neutral axis. Where do you think it is? Lower, in the lower half or the top half? The lower half. Okay, good. So we're not halfway there, but we know our neutral axis is down here. Now, there are two ways you can tackle this. What we'll do first is we'll find the neutral axis. Find the neutral axis. So you can say it's the big rectangle, take away the little rectangle. And I'll write the formula out again. YC, let's work from the bottom. So YC is equal to a sum of area, I'll just write area I, and that means area 1 times Y1 divided by, instead of writing sum of, I'll just write it as the total area. So you can actually say it's the big rectangle, take away the little rectangle, or if you wish, you can actually work it out to be 4 rectangles. I know which way I prefer. Which way do you prefer, way 1 or 2? The first one, there's only 2 rectangles. So could you just maybe just write out your values of area and y to check you're on the right track, and then I'll be the calculator for you. It is, sorry about that. That's 60. Oh, we're not calculating R yet, we're just calculating YC. So hopefully you've got your first area, 100 by 200. The distance from our data point, the bottom, was 100 mil. Then we take away our 60 by 60. What did you get as the height to the centroid? Hopefully you all got 130 mil. And that total area will give you a YC value of 93.44. And please don't just believe that, because if you had pressed the wrong button on your calculator, maybe you would have got 120. So go back to your shape and go, 120, hang on a minute, that puts it in the top half. I think I've made a mistake. I'm going to plug it in my calculator again. So 93 places it in the lower half. So pretty confident we did it right. Are you confident? I'm confident. So what do you think I'm going to want you to do next? Calculate I now. Just set it all up. So shift. So my formula, I is equal to a sum of all the BD cubed on 12s plus a sum of all the shift square terms times their areas. So let's refer to this as area 1, and that's our area 2. So what is shift? That's why if you draw it roughly to scale, you can see straight away what it is. Shift is the distance between the section neutral axis and the centre of your section. So that value there is shift 1. So once again, shift is the distance between the section centroid and the centroid of the rectangle you're looking at. So that value in there is shift 2. So what are those two values? We know that's 93. So shift 1 would be the distance to the centre of that rectangle. It's just 100 minus 93. Does that make sense? Shh, you're talking about another subject. I know you are because you're on the computer. Shh, not so loud. Shift 2, please. Shift 2 is the distance. So the distance to the top here was our 130, and from that we take away 93. So we have our shift 1 and our shift 2 values. So I now, that's 100 and that's 200, is the sum of all the BD cubed on 12s. Remember, B is the dimension parallel to our moment of inertia. 100 by 200 cubed on 12 minus 60 by 60 cubed on 12. That's the sum of all my BD cubes. And then here I would say plus area 1. Just so I don't write all that out, I haven't got the value of it. That's shift 1 squared. Now, where do 5% of people always go wrong? I'm telling you now so you don't make this mistake. remember to square shift. In the class on Thursday, in 2 weeks' time, I'm going to go around and then they're going to go, I got it wrong, and I'm going to go, you didn't square shift, and they're going to go, oh yeah, okay? So now, remember, square shift. So this final term I would subtract, because the area I'm dealing with is a subtracted area. So that's 60 by 60. Well, I will write the whole thing out here because I have room. So you square that term. So it is just simply a matter of doing some problems. Now, if we wanted to, and I will set it up this way as well, I'm going to break my section up into these 4 rectangles. So when we break it up like that, we would add all our terms. So that one's 200 by 100. And that one in there is 60. And these here are 20. And that bottom one is 100 by 100. So if I was doing it this way, I will get the same answer. And that answer, which I didn't write up here, is 61.6. Yep? You're righty. That should be 40. Is that what you're saying? Yeah, thank you. And the bottom one is 100. Oh, thank you. I need glasses. Now, I'm going to erase that because that looks messier than my usual messiness. And what did I put them in black? So thank you. That's 100 and that's 40. So this time round, I'm just showing you different ways of doing it. 100 times 40 cubed on 12, plus 2 times 20 times 60 cubed on 12, plus 100 by 100 cubed, so I'll just put to the power of 4 on 12, plus my top area. Has anyone worked out what the shift is of that top area? It would be the distance, 180, minus the 93. Can you see that? Because the distance from the bottom here, that distance in there to the centre is 180, and our neutral axis is down there, and that's a really bad colour to use, 93. Can you see that? Okay. So am I going on and on about this? Yes, because you still get it wrong. So our next area, 2 times 60 times 20. What is shift this time? The distance to the centroid there is your 130. Minus your 93 again, all squared. And the final area, 100 by 100. Yes, this centroid is below, but remember we're squaring it. So this time round, 93.414 minus 50, all squared. And of course, when you do that, you'll get the identical I value. Now, in saying you have to know this all your life as an engineer, you have to know it for first, second, third, fourth year. But generally speaking, you look up section tables and you get the values out of there. But you still do have to know how to do it as an engineer, really, because you can see a lot of big sections are made up of plates. So quite often we have an I-beam that isn't quite big enough. So what we do is we stick a plate on top and we weld them together to create a stiffer section. So you need to understand how to work out stiffness for all those. Okay, so I'm going to work through an example again on here. Because my neutral axis now is no longer in the middle. In this question here, it's the same loading as we had before, the same neutral axis position. Well, we can work them out, or we have worked them out. What is the maximum tension and compression bending stress? Now, once again, in the exam, on the test, people see tension, compression, stress, and they come up with P on A. When you see its lateral load, you know it's bending. You know it has to be the MY on I formula. And we're referring to the tension bending stress or the compression bending stress. So you may get asked what's the maximum tension stress and what's the maximum compression stress, but they are bending stresses. Okay, this one we've worked out the moment of inertia in the previous PowerPoints. We know the stress at the bottom will reach yield first. We've got our bending moment diagram. Now, just be aware, here is my formula. To find the maximum stress, it's not just moment that has to be maximum, it's actually that top line, m times y, that has to be a maximum. Now, in our example as drawn here, if I draw the deflected shape here, exaggerated, we have tension in the bottom and tension in the top. Now, my maximum bending moment is the 80. However, when I look at my section, which is my T-beam, at location B, here, which side have I got tension in, the top or the bottom? Top. So here is where I have tension. However, if I now go to location C, where have I got tension here? At the bottom. So can you see these Y values that we would use are different? So it's not enough that you find the maximum moment. You need to find the maximum M times Y value. And this type of question is quite often put on the exam. So what you would have to do is you would have to, at B, calculate the stress in the top and the stress in the bottom. And at C, calculate the stress in the top and the stress in the bottom. This is the easiest way without thinking. You have 4 stresses and then you work out which one is the maximum. So in this problem here, have a look at B when my moment is M. I'll call them now tension and compression wise. So at B, we said here that we had tension in top. So therefore, my Y tension is 151 and my compression is 365, and we get 2 stress values. When we now look at C, location C, this time round, you can see Y tension, because we have tension in the bottom at C, the Y value is the opposite Y value. And thus, when you work out the 4 corresponding stresses, the maximum compression occurs at B and the maximum tension occurs at C, which isn't what you would first think if you were just looking at your bending moment diagram. If your section's symmetrical, Y is always the same, you just find where your moment is maximum. If your section is not symmetrical, you need to be aware that you're looking for the combination of M and Y. Let me show you something a little bit more interesting than that. Any questions? Okay. So I'll pause there and show you something to make you think it's worthwhile listening to these lectures, because one day I might design or work on a project like that. Has anyone been there? Anyone? I haven't. Stunning bridge. It's the tallest vehicle bridge in the world. So this deck here is 343 metres off the ground, taller than Eureka Tower. So I should turn all this off when I say if you're going to jump from a bridge, this would be the one. They'd probably take days to find where you landed. I'm down there in the scrub. Anyway. Okay, I'm not always politically correct. Okay. Stunning bridge. It is a... sorry, what have I got written here? Sorry. So we have our engineer, Michael, I can't pronounce that, I'm afraid, Villauguer, and Norman Foster, who is nowadays a Sir Norman Foster. He is a very well-known British architect. So an architect was there in the actual conceptual design, but the engineer would have had a huge input here in actually making that sketch stand up. So this is what we call a cable-stayed bridge. So you can see all these cables here are supporting this deck. So how did they build the damn thing? They started at the bottom. And they slowly use what they call slip form, where they have the formwork, they pour the concrete and then they move it up. And then they pour more concrete and they slip the form up. So you can see the columns growing. And you can see the seasons changing. Look at that crane. I wouldn't want to be that crane driver. He could get paid whatever he wanted. Imagine if you had to climb up there every day. Don't they say that crane drivers don't go to the toilet, that they have a bottle in there with them because it's too hard to... Does anyone know a crane driver? If you do, could you ask them and tell us in week 8? Anyway, here it's winter time now. So as you can see, this took a long time to build. So we've got all our columns. How the hell do we get this deck? So you can't say let's build the deck on the ground and let's lift it 340 metres. How do they get the deck on this thing? Oh, it goes higher. They slide it out. So they built it out to the side. So when you looked at those pylons, you thought they were a continuous pylon. They were actually built continuous to the underside of the deck. And then this whole deck and top pylon and cable stays were built out to the side. And then you can see in here a temporary prop. So to expect it to span the full distance is too far. So they have this tower here that picks up some of the load, and they slid it out, and they used hydraulic ramps, and they slid it out at 400 millimetres every 4 minutes. So it was a very slow process. But you can see we're above the cloud line there. Isn't that cool? So there it is making contact with the first temporary scaffolding. Look at that. That's cool. There it is with the pylons just about to meet up. There the engineers walking under. This would be where they push it out with the rams. So it's a steel deck. Now you can see a wobble in the deck. So it's a steel deck, a bit of a wobble. Once they got it all in position, then they would start tightening up the suspension cables. So in a structure like this, one of the principal load cases isn't just dead and live, it's the construction phase. It's okay, we have it hanging out there. What's the force in the cable when just before it touches the next support? So a main loading case here would be the actual construction of it. And there are the cables there. Don't know how many there are, but the main deck weighs 36,000 tonnes, so a lot, 36,000 cars. So the cabling would be very strong. You can see the wobble in the bridge still there. You can see them sliding it out. We haven't made contact yet, and that's it. So you need to know how to calculate moment of inertia. You do. You do. Sorry? Oh, last slide. Oh, okay. This is taken, I think, with a fisheye. That's why I said, has anyone been there? I think this is taken with a fisheye lens, a curving lens, because I don't think the bridge is that round. So I think, you know, or a panoramic view. So it puts that false curve into it. So you can see the river's here. So if you're going to jump, try and hit the river. Or you know when you drop things over the edge, it'd be great going, you go down there, I'll drop it. Of course, I imagine you are not allowed to stop the car on this bridge, and I imagine you would get fined enormously, so I am in no way telling you to do that. Yep. So you don't fall asleep. Well, there you go, it is, isn't it? I didn't tell you how long it is. It's 2.4 kilometres long overall. It has 8 main spans and 7 masts. There you go. So, let's get going. What I'm going to do for you now is I have 2 examples. We'll only finish one today. We're going to work right through, calculate reactions, draw shear force diagrams, draw bending moment diagrams, calculate moment of inertia, and calculate bending stresses. So this covers everything on beams we've done. So the question is, calculate the location and magnitude of the maximum tension and compression bending stresses in the beam below. So, which one have I given you first? That one. Okay, reactions. We have 4 unknown reactions. Oops. So I'll try and be neat, so you can just rely on my inkings. AX, AY, BY, CY, OMG, there are 4 unknowns. Don't panic, there's an internal pin. So, because there's an internal pin, we know we need to split it either side of the internal pin. So I've got it here. So I'm just going to draw it a little bit apart. So which side? Yes. How did you know what I was going to ask? I'm already being messy. We start on the right-hand side. To calculate CY, or PY, whichever you want, let's calculate PY first. So let's take moments at C. So I will run through every step, even though you may think I know how to do that now. That's great. 40, so taking moments at C, looking to the right of the pin at our free body diagram, you would say, well, I have 40 times 0.5, it's going anti-clockwise, then I have minus PY times 1.5 equals 0. So from that, I get a value of PY equal to 10 kilonewton. And so knowing this force here equals 10 kilonewton, just tell me what CY equals. Can I leave that bit out? PY times 2, thank you. Yeah, okay, good, you're on the ball. I knew that. Thank you. And I've got 2 written on my page too. So PY is equal to 10, so you know CY is equal to 30. Now at this point, you could go back now just looking at it as a whole. So now we have 30. We can go back to looking at it as a whole. Oh my God, there's an internal pin in there. Remember when you're doing equilibrium, you can take all the structure away. It doesn't matter what the structure is. You're just looking at balancing forces in the X, Y, and moment direction. But I won't do that. What I will do is I will continue to the other side of the pin. So now my pin force is 10. Now, what is that? That's actually a shear. And you know shear are equal and opposite. That's why when it was up on the right side, I draw it down on the left side. When you join it up, that's just considered a shear force. If you would pull the pin up, I would have to push up with one hand and pull down on the other hand to keep it together. So it's a shear force. So I have 10 kilonewtons here. I have BY, I have AY, my UDL load. I'm going to now take moments at A, and they equal 0 because my system is in equilibrium. So my total UDL load down here is 2 times 3, and it's acting in the middle of the loading pattern, 1.5 metres. Then I have my unknown reaction, By, it's 3 metres away. And then I have my 10 kilonewtons. Now I've broken it up there. You can think of that 10 as if it's a force. So 10 times 5, all of that equals 0. From that I get a value of By. And then looking at forces in the y direction, I will speed this bit along now, you would get a value for AY. And of course I can't make this problem simple, so AY is actually negative. So what does that mean? It means this 10 kilonewton applied out there is actually pulling down so hard it's causing that support at A, it's causing the beam to want to flip up. So the support is pulling it back down. Okay, now let me just see how many more pages I have. Okay, that's okay. Okay, so what I'm going to do now is I'm going to transfer those reactions over here, and I'd like you now, and I will give you 5 minutes to draw your bending moment diagram and shear force diagram. Be it only the shape. So, at 2:38, I'll talk again. I'll just tell you, I'm drawing the arrow down here at A to indicate it's down. So I know you can't put values to it, just try and get the shape. Well, you can if you have your calculator out. And don't insult engineering by using an iPhone calculator or a phone calculator. One more minute. I forgot to put this equation up here. V is equal to dm dx. So this shear force diagram is also equal to the slope of the bending moment diagram. Come on, 2:38, then I can start. Change clock. Hey. So you all stepped down, didn't you? Yes. 3.66, that's the start, 1 point. Then the load reduced further, or it dropped further by 2 kilonewtons per metre. So that means a total of a further 6. And that should be straight, and it looks a bit curved. Let me just... Now when you do these, it's very important you try and draw them to scale. So if that's 3, 6, 9, that's 9. So hopefully you all got 9.66. Then you stepped up 19 to a value of 10. Shh. There's nothing happening through here, so we just move horizontally across. There's an internal pin, who cares? But hang on, have a look here. What was the shear in the internal pin? It was 10. And our value of shear through here is 10. So it all ties in. Then we step down a value of 30. I don't have enough room here, so I'm going to show it dashed. So 40 to a value of 30. Thank you. And then we step back up and we end up at 0 and we go, yes! And of course, if you don't end up at 0, you go, okay, I'll be honest with myself, I've made a mistake and I have to fix it. So at this point now, I might just work a couple of areas out because we know that will help us calculate some bending moments, because we can calculate some bending moments from looking at the integral of V, which is the area under the shear force diagram. So that area in here, area of a trapezoid, the average of the heights divided by 2 times the 3 metre width, so that's about 20 kilonewton metres. I'm going to break this area up into 2 parts. Area, I'll call that area 1, area 2 and area 3, so that's equal to 20, that's equal to 15, and to be precise, minus, minus. And this final area in here is also equal to 15. So, now, when you think of the shear force diagram, I don't want you to think of it as being a shear force diagram anymore. It's the slope of my bending moment diagram. My bending moment has a slope of 3.6, and that slope is getting bigger and bigger and bigger. Now, firstly, sorry, it's a negative shear force, so which way is my bending moment sloping? Up. So I've got an up, and I know it's a down, and I know it's a down, and then I know it's an up. So I put those lines in first. Where do I know my bending moment is 0? At C, at A, and at the internal pin. So I'm doing well here. When my shear force is constant, my bending moment is linear. So I'll draw this one in here. When my shear force is linear, my bending moment is a parabola. So the first question you might ask yourself is it a sad or a happy? Bending moments, when your vertical load is down, are always happy. But if you didn't remember that, oh my God, is it sad or happy? Look at this value of shear force. That represents the slope. I have a slope of 3.66 and my slope is getting bigger. So it has to be happy. If you draw a sad bending moment diagram, can you see at this point here, that's where your slope is maximum, and then it's getting smaller and smaller. So your shear force diagram will tell you if your bending moment is happy or sad. Okay, now from this point here, it has to pass through 0 here, and it has to be straight everywhere. It has to be linear and straight. So now I just go, okay, well, I just draw a line through here. Now that line, and I haven't drawn this to scale very well, that line has to run continuously because the slope of this line is 10 and the slope of that line is 10. Because my bending moment, from my shear force diagram, I can see both values are 10. Can you see that? So when you draw these, you are expected to draw them, I say to scale, but in proportion. You draw them in proportion, everything works out. So the moment here, once again, very easily, I want to know the moment there. I can draw my free body diagram, cutting it at 0.5 metres, and very easily here you can tell me what the moment is. 30 times 0.5, 15. And that happens to equal negative area 4. Remember I said if you come from the right, you take it as a negative of the area. So whether you choose to use equilibrium and free body diagrams, you get the same value. So what is this value here? That's area 1. So that's equal to 20 kilonewtons metres. In this instance, it would be harder, but you want to know what the moment is. That's meant to be a down arrow. You can cut the beam here at 3 metres and actually calculate the value. But it is easier. And that's it. There's your bending moment diagram. So we have a 20 and a 15. Now, before we go on, try and sketch the deflected shape. You'll get asked to do this in the third test and in the exam. What are you going to make use of? The fact that you've drawn your bending moment on the stretching side of the beam. So that is telling us when we look at our bending moment here that, let's find another colour to do it in, that's telling us, no, I want to do it in green. I have tension on the top because my bending moment is on the top. I have tension on the top, then tension on the bottom. I'm drawing it above and below the line, and then tension on the bottom. So what's that deflected shape look like? You can't tell me what actual values are yet. You're going to learn how to do that. You can look forward to doing that. So an easy way to actually look, appears quite complicated to work out the deflection shape. If I go back here to where I split it at the pin, If you knew you had a load down here and that reaction was downwards, you know that your beam is deflecting like that. In this case here, we put a load on it with two supports, it's deflecting like so. So if I had to draw the deflected shape, very exaggerated, I draw it coming down like that, and that's an internal pin. So that's the only time you'll get a kink in your deflected shape, other than when your beam breaks. So, did you all imagine that deflected shape? Can you see the logic behind it, how it works? I have tension on the bottom here, and I have tension on the top here. So I use my bending moment diagram. So sometimes you can use your bending moment diagram to help you with your deflected shape, or you can use your deflected shape to help you with your bending moment diagram. There's no right or wrong. You go the full circuit. You do one, you check it all agrees, everything agrees. Okay, we've got our bending moment. We've got time now to work out some stresses. In saying we've got time to work out some stresses, we have to work out the moment of inertia. We don't have time to do that. Can I ask you to promise me that you'll do it at home? No, you're just going to lie to me anyway. How do I know that? I have children. And they're on school holidays. And when I say to my son, what have you done today? He's not going to tell me he's played on his iPad all day. He's going to say, I read. So he will have read for 15 minutes and iPadded for 5 hours. Sorry. Has anyone actually done 2048? Has anyone got to 2000, has done it? Is there a trick to it? I can get to 1024. So I know you go side to side only, you don't go up and down and side. Can you come down if you know, can you come down and tell me after the lecture? Because if I do it before my 12-year-old son, he's going to be so pissed off. Okay, could you all attempt, and please, when I do ask you to do this, it is for your own benefit, and we have a break, a 1-week break, to calculate your moment of inertia, sorry, your centroid to be 35, and your moment of inertia about the x-axis. To have that value. So now, let's go back to, I'll draw in here, oops, sorry, my deflected shape. So why do we need to know deflected shapes? And I need to actually draw my bending moment diagram as well. We've got 5 minutes, we can do it. So there's my deflected shape, and here was my bending moment diagram. So remember, we had a maximum value at B of 20 and a maximum value under the point load of 15. Oh, not 5 more minutes? Exam. Oh, what one? Okay, wish him good luck. Good luck. Oops, that should be passing through 0 here. Okay? Okay, so, tell me, at B, where have I got tension? In the top or bottom? I have tension in the top. So when I work out the stress at the top, it'll be a tension stress. So, at B, in the top, I'm going to have my moment of 20. M, Y value, my Y value in the top here. Is 35, and and I'll just write I, and that will give me a value, oops, that's not meant to be 40, that's meant to be 460 MPa. And that's my tension force. So at B, in the bottom, this time round, our Y value is 64, and that gives us, bye, Happy Easter, if you celebrate it, a compression stress. Well, no, I didn't mean that really, I just mean if you do. But whatever religion you are, happy chocolate eating. Okay, so now we're nearly there. At, let's call it D. Where have I got tension? Come on, stay with me. Where is tension at D? In the bottom. Oh, just a few more minutes. You can't all say you've got an electrical exam. You do? Oh, okay, good luck. At D now, in the top, my moment now is 15. So my moment is smaller. However, in the top of the beam, where my Y is that, I end up getting a stress of 345. And this time round, that's my compression stress. And now, doing it in the bottom, I get a value of 633.4 MPa tension. So looking at those four values, tell me, where is my compression bending stress maximum? At B. Where is my tension bending stress maximum? At D. And that is a classic exam question. And I don't mind saying that because it means you'll then study it and get it right. So because of that combination of MY, because our section is asymmetrical, and that combination of AY, it moves the maximum values, tension and compression, to different points. Okay, happy lots of Easter egg chocolate eating.